several categories of pathfinding algorithms. What is this one?
I don't know the name of this one. I am not good at picking out academic names from implementations.
So this is, it looks like I'm having a hard time finding the part because like basically they got to introduce things that come from several different courses all at once. They're talking about a graph data structure that they seem to have just rolled themselves out of arrays. And so you've got data structures where it talks about graphs right at the end.
Graph is it like Facebook?
Graph is
structure,
in
or-
networks of vertices.
Okay, so like what Facebook uses, right? That's the database implementation for Facebook.
No, this is, so
No.
Facebook has something called the Facebook graph, but that's,
Under it's a graph database, like this person is related to.
okay, that is what this is talking about.
Yeah.
Yeah,
So,
yeah, that's-
that's exactly right.
That was.
So underlying Facebook
Oh, I know.
graph is in fact a graph database. There are multiple different types of graph databases. The big one out there now is called Neo4j, if anyone's ever used it. It's a lot of fun, but anyway, this is essentially creating a graph database in a JavaScript array, and then creating our own methods to find shortest paths through it, which is terrifying, but anyway.
Yeah, that might happen.
So like the graph data structure where you've got like the vertices and then the relationships, and in this case the relationship is just like a geographic relationship. You can move from here to there.
Okay,
Okay.
weights or
But,
distance or
but
whatever.
yeah, with the distance, exactly. The algorithms that run on top of that thing are some of the more complicated, more heavy algorithms. They quickly go into the O(n) squared space, and like if you're asking for optimizations, there are some NP complete problems in graph processing. Actually, there's lots of them. So they are some of the most complicated to solve algorithms that are out there. On top of that, there are some really brilliant guys who have done some really cool shortcuts in processing certain kinds of problems, like shortest path. Okay, and so I'm pretty sure they're using Dijkstra's algorithm. Dijkstra. I can't pronounce that
I
last
don't-
name.
I don't know either.
Especially since they started with a quote from him. It's impossible that they wouldn't know who he was. But you know, actually, some of this looks like it may just be doing brute search too.
Yeah, I actually think this is just boot search. I don't think this is like.
Yeah, it's doing brute
Okay.
search. And
We're not going to go over find route all that much. That's my conclusion because I'm going to lose everyone, and I have no idea what this algorithm is. So we're just going to continue. We're going to start, and we're going to go through it. And remember, when we had the last stupid 5 problem, which I disagreed with the author, what did I tell you? A big part of a computer program, being a computer programmer, is simply giving the computer shit that someone else wrote. Normally, you do that in the form of a library, right? So normally when you're not writing shit and you don't understand it, it's already packaged conveniently and appropriately in a form that you can consume and use, right? Without you even being exposed to it. So you just simply call a function, you give it a graph, you tell it where you're coming from and where you're going to, and it does all the dirty work for you. That's how things normally work. We don't have a library. They haven't even taught us how to use libraries yet. They've exposed us with a big ugly function, and I have no idea whether or not, it's certainly not important as a programmer to understand how that function is working. So I don't know why I should waste that much time on this to begin with. So we're going to treat that function probably more like a black box. But if we want to go through it, I guess we can do that too. It's just, I have a hard time when I have to always open these black boxes to explain to you how some guy wrote a random function that traverses a graph to come out with what he believes is the shortest path. You know, Ed?
It's using an unweighted variant of Dijkstra's algorithm.
There you go. I mean, I've seen Dijkstra's algorithm. I'm still not sure, but you know, whatever. The point, it really doesn't matter, is the thing. So, and anyway, let's go through it. All right. So, Before we start going through it, I'm sorry, we still haven't gotten this guy assistance. If anyone wants to help out with the Linux, it's always, voluntary basis thing.
I'm actually already helping.
Oh, you are?
You just don't know that.
I didn't know that. I'm sorry.
Yeah.
By all, I'm just happy you're getting someone takes care of it.
Background mode too.
There we go. He's got it all taken care of. He's a good guy for the job. I just didn't know. Okay. Very cool. So there is code available online. Let's rehash that. Remember, the examples that we're seeing in the book are not the entire data set. And even if they are, we shouldn't expect that, because I've seen prior cases where I know that to not be the case. So if we go online and we pull down this Eloquent JavaScript and we go down to the code sandbox, it's eloquentjavascript.net, and then we come down here to your code sandbox and exercise solutions, we can select 7, which is our robot, and we have 2 links. And one of them is a nice little web display, which we will use. It has some explanatory power. I like it a lot. I am not at all going to explain it, but the code is available, and you can actually see a graphical implementation of everything we're doing today. But the one that we want here is this one, Chapter 07 Robot. And if we click on that, we'll see a bunch of code. And this is the code I'm going to explain and copy and paste and show you how it works. All right.
Make that bigger.
Yes, definitely. Okay. So starting off, some of this I'm going to go through the book exactly, and some of it is just going to be me talking about what we're looking at here, because code is what matters. We have roads, right? This roads is what kind of data object? Welcome, my girlfriend. Lumine, you can sit anywhere you want. It doesn't matter, but I'm certain there's space here. So we have this array here, right? This is an array. An array is an ordered list of elements, and each one of those elements in this array has essentially 2 places separated by a dash, right? So if we look at this first element, we have Alice's house. That is the starting location. And it's going to Bob's house. That's the ending location. So that's very simple. It's not the best way to store that information. It's the way the author's chosen to store that information. So we have probably, like, let's say 12 things there, or whatever, maybe 15, something like that. And each one of them is a starting location dash ending location. We have this function called build graph, and what is it going to do? It's going to take this array, and it's going to split it right here, right? So we're splitting the array on that dash. Okay? So we split it to get the starting location and the ending location. We call it from to. I really, really am fond of the name from and to. It's very self-explanatory. Unfortunately, he loses that in the rest of this paper, and he goes into place and address, which I find absolutely ridiculous. But we're looking at build graph, and we're taking this array, which is edges, right? We have the edges up here, which he calls roads. Again, we're just randomly switching terms. Peter made an argument earlier that the terms are stupid. They are, but I'm trying to explain his right now. These are actually roads. In graph theory, we call a list of things that take you from a starting point to an ending point edges, right? And here's the catch about an edge. An edge is always one direction, right? That may be his reason for giving it a different name. Roads, you can, in most roads anyway, you can always drive the opposite direction, right? So you can go from the marketplace to the town hall, or the town hall to the marketplace, but if it was an edge, you could only go from the marketplace to the town hall. You wouldn't assume the opposite relationship is true. Okay? So, yes?
I didn't quite, when you said edge, would you draw, I'm not getting that one.
Edge is a terminology that comes from the graph database parlance, right? And an edge is a relationship between 2 nodes, right? So that relationship is not, and I don't know the actual right name for this right now, but it's not bilateral, it's unilateral. Is that correct? Or unidirectional? There we go. It's
Directed versus undirected.
It's not directional or undirectional. It's not directional. That's right. In graph theory, it's directional. In his array here, it's not directional. So he has this array of roads, and then when he has this function build graph, and in build graph, rather than saying it takes an array of roads, he uses the graph term edges. I just want you to understand where the term edges comes from. If you have a graph database, you call the insertions into it They're insertions of edges. That's what they are, right? So what we're doing here is, let's take a look at this. We're creating a graph object, and we have this function inside of it called add edge, right?
That's the function I was telling you about.
Okay.
It's like a fully defined function.
There we go. Some languages don't allow this. I'm going to explain what Jared's talking about. Some languages don't allow functions inside of functions. C is a great example. In C, you can't do this, right? So in some languages, you can do this. In some languages, you can't do this. If you're not used to languages where you can do this, it's definitely weird, right? But in JavaScript, you can do this, and you can do this because all functions are just function objects, which just have variable names, right? So this is essentially the same thing as saying let add edge equals an anonymous function. It's no different. It's just the syntax structure of it. So yes.
So is it actually scoped to build graph
It is.
only, or
Yes.
it is? Okay.
It is. That is exactly right. Okay, so we have this function inside. If anyone has any questions, by the way, throw your hands up. We have this function inside of build graph called add edge, and it's taking from and to. Now notice, this is an abstract function at this point. We could call this outside of it too, right? You have a function, it takes a from and a to. We got to do something with it. So what we're doing here is this graph object above, we're storing on it from whatever the first parameter we provide is, right? So you're taking this argument from, and you're going to store graph and then the first location, that from location. And we're going to essentially say if it's equal to null, right? If there's nothing provided in that first variable, then we're going to say that if there's nothing there, right? That's a better way of thinking about that. If there's nothing in this, if this graph doesn't have anything there originally, let me step back a second on that and be very clear about what it's doing. We have an object which is storing locations we're coming from and going to. If it doesn't already have an entry for the location we're coming from, that's what this is triggering. If it doesn't have the location that we're already coming from, it's going to create a to array, right? An empty array with one element. But if we already have an entry of places we're coming from, right? It's going to simply add it to it. So this whole piece right here is simply saying if I have no entry for that location, create it. Create me an array with one entry. If I already have an entry, simply add that entry to it. Does that make sense to everyone?
It's actually a pattern you see often called upserting.
That's exactly right. Yeah. So this is a pattern you will see all the time. You essentially, if you don't have an array, at some point you have to initialize an array. You can't push to shit that doesn't exist, right? So you have to say at some point, if nothing exists, create me something that I can later push to. And that's what this is doing. So you will see this all the time. Most languages have some variation of it. Okay, so we have this thing called add edge. And all add edge is doing is taking two arguments, and then it's simply adding them into this graph, right? Now, one thing we should notice is, I told you earlier, what did we say roads was? Roads is non-directional, is undirected. There we go. I'm going to check these words later, but anyway, we'll fly with them. Roads is undirected, which essentially means we can go from marketplace to town hall to marketplace. Now, we were building this database here, this graph database, which is clearly directed from and to, one direction, right? So how are we going to do it the other way? Okay, we'll come down here. Let from to of edges.map split, right? So what we're doing here is we're taking that thing, we're splitting it on the dash, we're assigning the first and second part of that, the stuff that comes before and after the dash, to the variables from and to. And now look what we're doing here. See this? This is what makes it undirected. So we had roads, which is undirected. We have add edge, which is directed. And now what we need to do is add an edge from both the start to the end and the end to the start. Because we got to be able to go both ways. We've got to be able to traverse all those locations each way. So we do that here with add edge and add edge. We're calling that twice for that reason. All right, does everyone see that? Any questions? All right.
Is the R for reverse?
Is the R for, no, the R is for element. So what we're doing is,
I'm guessing trying to mean road.
there we go. The R is for road. That actually makes more sense. It's each element of that array, but it's a road. So we're taking it here, edges.map. By the way, this is also not very good. We should file some advice on this. But anyway, we're taking this whole edges, which is that network of roads, and we're mapping over it. And for each element in that array of the edges, we're saying split it. That's how that's read. Right? So this is a function here for each element that you get, split, and return those two elements. And that's what this is. This is that destructor syntax we saw in, I think, chapter 3. So when we call split, we get an array of two elements. And then this right here, the from2 thing, this is actually pulling out both of those elements. So we have simple variable names for them. Okay. Does that kind of clarify that, Peter? Okay, cool. So edges gets put up at the top. That's what comes in as an argument. And then we use it down here. We call edges.map. Now, why do I think that's slightly confusing? Can anyone take a guess at that? Here, I'll just... It's confusing because traditionally, when you're writing a program, you don't use map unless you want the results, right? So to give you just a general pointer, map takes an array and it iterates over that array. And for every element in that array, it calls a function. But it returns the values, right? So it's kind of weird to see map where you don't care about those values, right? Normally what you would do is you would just call edges.forEach. That's the more right way to do this, if you ask me. So you could say here edges.forEach are, and then do this stuff, and then that would look cleaner. It would just be easier to follow, in my opinion. But anyway, we're calling this here road graph. We're essentially creating now another global. So we have our first global, which is all of the roads, right? And now we have road graph, which is the graph database we create from the roads.
So let's take a look at it, because I don't think he even shows it to you in the book, which is somewhat disturbing, right? So if we take it, right, we're going to clear that out, pop up node, scroll up to the top. We're just going to copy and paste all this garbage in here, which we hopefully understand. No questions. So everyone gets it. My explanation is flawless. Then I call road graph, and I see all this stuff. Okay, so what is this stuff, right? Let me make that bigger so we can all see that stuff. Make it a little bit bigger yet. Okay, hopefully we can see that. We have here, we have a list of all of the places we're starting from and where we can get to. So if we start from Alice's house on this top line, we can get to Bob's house, the cabinet, or the post office. If we start from Bob's house, we can get to Alice's house or the town hall. That's kind of interesting. So if we go to Alice's house, we can get to Bob's house. If we go to Bob's house, we can get to the town hall. So we can't go from Alice's house to the town hall directly. We got to go from Alice's house to Bob's house to get to the town hall. And that's how you read a graph database. That's what you're doing there. So you're trying to show how all of these things relate, so you can get from one point to a distant point that doesn't directly connect. That's what it's there for, right?
Well, in terms of the array, that's key value, right? You got your key and then your colon, and then your value is actually those three elements.
That's exactly right. That's exactly right. Yes.
This is the list of possible destinations from any given point.
Except one small correction. Is this an array? What is this?
An object.
It's
JSON.
okay. Hash table is actually correct, but we don't call that in JavaScript. What do we call it in JavaScript?
Object.
Object. It's actually not actually a hash table either, but if you're coming from Perl, I understand how you would leave that. These are different methods of storing objects. Objects are complex key value things in JavaScript, right? It's not just something that is an object like in Java or like in C++. An object is a key value store. So when I say what is road graph has the curly brackets, and we simply say it's an object. If it was an array, what would it have?
Square brackets.
Square brackets. So we have arrays in there.
Yes.
All of those values can be arrays, right? They don't have to be arrays. Actually, they do have to be arrays. They all have to be arrays. Because if you have one element, you make an array with one element. You didn't have to do that. That's the way the author did it. Just to clarify and redeem myself. Okay. So now we have this other thing. We're moving down. So far, I haven't used any of these, the book's text. I hope that that's working and we get this. If not, we can go back and review the text and read it and talk about it. If you want to do that, I'm happy to do it. If anyone has any questions about the way the author described things, we can examine that, and I can hopefully explain some of it. We have this thing here called village state. Okay, I used this word a while ago. We talked about functional programming. We talked about higher order programming. I use this word. And in fact, Peter caught me in the hallway and he said, we need to reduce this to 4 words. I said, well, those 4 words are not how we typically define things. This word you will see all the time as a computer programmer. The word is state, right? So having a very good idea of what state is will be very beneficial when you have to read and understand how other programming languages work. State is essentially when you look at your program in terms of the processes that it's undergoing, what functions are being called. All of those things being manipulated and stored in memory, we used to refer to as state. As we travel through this graph, we're going to have the location of where we're at and where we can go. And that is the state, right? We can travel somewhere else, then we've modified state. We have a new state. We're starting from a new location with a new environment, right? When we say we have globals, right? Globals store state. That's what they do. The problem with globals isn't that they store state, because everything has to store state. You have to store it somewhere. You can't just get rid of it, right? The problem with globals is that the scope in which they store that state is removed from where the work is being done. So you have other things that can modify them, that state, and you have to keep in track everything that can modify it, where all of that stuff is. You want to have control of state. You want to keep it local to your program. I just want people to be exposed to the state word. Because if words are a problem, this is a word we need to understand. Right? This is a word we got to use. So we have this thing here called village state. Village state is a class that represents where we're at and where we're going, and it provides one, what do we call this? What is move? Anyone want to give it a shot? What's the right word for move? Method. Method, precisely. What is a method? You want to try that one?
A function in a class.
That's exactly right. Nothing special about it. Were you at the last class? All functions get what?
Mash on tab.
No, that's okay. Very appropriate.
Right.
I said, when in doubt, my answer is mash on tab. And it often is.
That was good.
That was that. I do like it. 1 point for style.
Correct.
All functions in JavaScript. There we go.
Get a this.
There we go. They get a this, right? And this is a place where you store state. This is an implicit method of passing around state from one method to another. That's what it is. So when you have an object, the object is stored in this. When you call a method, methods get this. That's what stores the state. That's the way to think about it. When you move away from object-oriented programming entirely, you do so because that method of storing state in this becomes somewhat problematic. And that's for all different reasons, which we're not going to get into. But we are going to get back into state being this. So move is a method. A method is a function that expects a this. So what are we doing here with move? Well, let's just look here really quick. This is not parcels right there. If you call move, you don't pass in parcels, right? So if you're not passing in parcels, where is it being stored? It's being stored in this. This is your state. I just want to keep reiterating that. I want to drive some of this stuff home with object orientation that I may not have hit home in the last class. So we have parcels, which is being stored in.
No, they're cleaning pretty early, huh?
Yeah, I think maybe we should close that door. You want to get to know someone? Okay. So
That's going to lock it.
huh?
If it starts up again, I'll hop up and close it.
Ah, okay. Someone's making margaritas or cleaning the floor. I'm not exactly sure what pitch of motor that was. Okay, so this parcels we see is actually defined in the constructor. So the constructor for an object, again, we're going to rehash some of those old concepts and ideas because we just covered them one class ago. You may have limited experience with it. The constructor is what sets up the state for the object, right?
So when you say I need a new object, something has to set it up with initial values. That thing that constructs it, sets up the state, is the constructor. In JavaScript, you simply declare it by using the word constructor, which looks like a function, and it is. It's a special function. But it has access. It's the first function that gets a this. And then it can play with the this that it gets. So here it's taking its this, and it's defining a place property on it, and it's setting it equal to place. And it's also defining a parcels object, and it's setting it equal to parcels. So the second you call village state, you're going to be giving it a place and a parcels, and then every subsequent method you call has a this in it. And that this has access to the place and parcels that you constructed the object with. Okay, I hope that kind of where this is starting to all pull together, how object orientation works. So, village state is going to take two things, place and parcels. Now, problems I don't like with this curriculum and this whatever method he's got going on here. We don't know what place and parcels are. That's kind of weird, right? We know it's taking two things, place and parcels, but we don't yet have any idea of what they look like or what they do. We don't know if they're arrays. We don't know if they're objects. We don't know if they're strings like the roads were, right? When you're talking about a language like JavaScript that doesn't have types, you don't know what you're going to expect with it. So you essentially, we got to look at how it's being called to determine what those are, right? And we got to look at how he's using them to make those inferences. So in some languages, you have to type it. You have to say place is an array, place is an object, place, whatever. You have to describe it. JavaScript, you don't. So we have to reason about it. We're going to have to do some detective work. We're going to look at how it's called. We're going to look at how it's used. And we're going to figure out what place and parcels is. Okay. Yep.
This is, I guess, a more general question, but for a programming language, why not type something, or I wonder why they made the decision with JavaScript not to have the strict typing? Does it?
Typing is more learning. It's less complex to maintain, but it's more learning to understand it. There's a whole class of knowledge that you have to use typing correctly.
And JavaScript comes from a history of programming. It's very tightly associated with web programming. And a lot of the really cool, we can write something really fast programs that fed into it are untyped programs, or they have only like one type like string. And so that meant that there was a point in time where people thought this might actually be even better. So there's historic arguments. So in summary, they're lazy. Well, that's a judgment call. It's actually a lot harder to write untyped code that's really, really well maintained and checked, because you don't have the compiler to tell you when you accidentally slipped the wrong thing into the wrong slot.
All great things in life have a return on investment, right? Doesn't matter if it's a relationship, if it's something you're trying to learn, everything's got a return on investment. Some things give you instant gratification, right? And they have no pain up front. And some things have slow and steady pain, and you get that back in the end, right? They're just different ways to invest time and education. If you want to learn how to become a computer programmer, how many people have done computer programming less than 1 year, right? Do we have anyone in here who's relatively new, has done computer? Okay. Adrian, what editor are you using? What do you use to write your code?
Sublime.
Sublime. Okay, Sublime is a really popular one for newer generations of programmers. How many people here are using Atom or Visual Studio's code, VS Code? We have half of the class now using this, right? Over that. I would say maybe 70%. This is why I think it's important for the Linux group to target newer audiences like JavaScript, because we're otherwise out of touch with that stuff. But the reality is that those types of new editors are not nearly as efficient or productive as something like Vim or Emacs. Those are your tried and true methods. Why don't people use them anymore if they're better? It's simple. The learning curve is like this. You're going to die at some point, right? You want to write code or you want to mess around with an editor. I'm glad they're out there, but they're just, That's how that works. So when you ask why don't people type, typing is very much the same way. You hit a cliff. You got to understand covariance, bivariance, all of this type of thing. In JavaScript, there's a project out there to kind of like bring some of those ideas to JavaScript, and it's codenamed Fantasyland because it's so abstract, right? So, and yeah, you're back in the world of functional programming and these very abstract notions. So, driving it back home, JavaScript is untyped. We don't know what place and parcels are. Could be an object in an array. Let's look at it. Let's try to figure it out. Okay, here's a place, right? So what could that be? Well, if it looks like that, it looks like it's going to be a string, right? So this dot place is a string. What about parcels? What is parcels? Well, here, we're calling this dot parcels dot map. We learned in the last class you can map over a string. But we hope that's not what he's doing. Because if you map over a string, you're mapping over characters, and that doesn't make all that much sense. So I believe that he's mapping over an array, logically. So place, string, parcels, array. That's what that looks like to me. Okay.
Well, place is a string, but it's also a key too. Like when you ran that the graph, it showed like a key and then an array. I think place is the key.
That's exactly right. Place is the key into that. That's exactly right. And parcels is going to be a list of crap. We don't know what's inside. Well, let's see. Maybe we can figure out what's inside of it. Okay. Okay. Yes. Here. So we know that parcels is an array, right? We know it's an array because we're mapping over it. We've already determined that. What do we know about the contents of that array? Anyone want to give this a shot before I ruin the secret? The contents of the array. You can have arrays of strings. You can have arrays of objects. You can have arrays of arrays. You can have arrays of symbols. You can have arrays of all kinds of crap. What is this an array of? Look at how it's being used.
Location?
Not the data inside of it. What is it carrying?
Object. It's going to be like a key
Okay, object.
value.
Object. We heard object. Why is it an object?
You can tell because it's saying key dot place.
Boom. P dot place. He's got it. So we have P, and we're iterating over it, and we're saying P dot place. Well, if we have a property on P, it's an object. End of story.
Okay.
Right? That type of syntax is an indicator it's an object. So let's be more explicit. We started off and we're saying what is place and what is parcels. We said place is a string. We said parcels is an array. It's an array of objects. We know it's objects because we're calling P dot place.
So P is a village state essentially.
Yeah, something like that. Who the hell knows? But it's got a place property on it, so it's more than we knew when we started.
The only thing we've defined that has a place property is that class.
I like that. Brilliant.
And we're also returning an object.
Okay.
That's also true.
So yes, anyway, well, we'll figure it all out later.
And that's how we do programming. So look, we have this thing called village state, right? We've defined it. And it's actually a variable, village state. I didn't define it. I only did verbs and no graph. It's not there yet. Jason has that right. Okay, boom. Now it's there. Okay, beautiful. All right, it says function because it's a class. Why does it say function when it's a class? Because we went over this in the last class. Class and function and objects can all be used to do the same thing in JavaScript, right? JavaScript doesn't actually have classes. It just has functions. Class was something they brought in recently with something called ES6. Under the hood, it doesn't exist. There is no abstract notion of class anywhere in JavaScript. It's a layer to make things prettier for people that come from languages that have classes. When you learn prototypical, or I said I didn't know that word in the last class, I should look it up because I'm going to use a word that probably doesn't exist in this class. But when you use prototypical inheritance, you don't need functions or classes. These are all just veneers. They're different syntaxes to do the same thing. When we saw object.create and it took a super class or something of that sort, that was actually a prototypical object that we're prototyping. We're using that, right? We went through some of that stuff. I think everyone got it then, right?
But in the event they didn't, that's what this is showing you. So village state is it's a returning function, but it's a class because it's all the same thing. Or rather, all classes are functions. And we can look here and we can see that it's a constructor. It's got a constructor, right? So let's see how we're calling this here. Okay, this is one of the things. The code in this doesn't have all the code in the chapter. I was kind of alarmed when I found that out the first 2 or 3 times. So it's actually bilateral. Not all of the code in the chapter is in the code he gives you. And in the code he gives you, it doesn't have all of the code in the chapter. Yeah. So we have this thing called village state, and there is actually, see how we have this thing here called first? I like this, because this is actually showing you how the village state thing works, right? So village state is taking this place here, post office, and this array of objects, which we already said had a place and an address. Right? We looked at that function, we determined what that looks like. So now we're going to call it, we're going to create our first village state, right? Let's pull this up, copy it, and paste it, because that's really 90% of programming anyway. Anyone who tells you differently is a liar. And now here we have this, right? Village state, we're seeing what it looks like. I'm just confirming, right? We're creating it with new. We're saying new village state. We give it the place, we give it the parcels, and then this is the garbage we get back, right? So far we've seen the roads, which were separated by dashes. From the roads, we took them in, and we made them into two-way edges. And now we've lost all of those names, and we have place and address. The place being where you're picking the package up, and the address being where you're dropping it off. And I really like from and to better than place and address. I don't know if we're here, but
I think it would have been really helpful if instead of saying P, he just called it a village state or something like that, so you know what he was trying to propose.
he calls it P because he's referring to parcels. So the parcels are the second thing here. So when he says he's mapping over, he's saying for each parcel in this array of parcels.
You're saying P dot place.
Right.
So P is place one of the.
Place is the property on the parcel object. This is an array of parcels.
Also, I should have called it like a parcel.
Yeah, well, you could have said parcels instead of P. That's right. But that's what the P stands for. All right. So we have this village state thing, and what can we do with it? Well, we know we have a method called move. I already asked the question, and we knew it was a method, and we're going to see what that works, how it works. So we have, let's look at this one more time. Village starts with the post office, and it has this list here of parcels, and now we're saying we're going to move to Alice's house. So we're starting off at the post office, and we have to get to Alice's house. And we're going to try to move it. Now, in functional programming, you want all of the functions to be pure. That's a word that was introduced in the book. Some people read it. What does pure mean? Anyone want to give it a shot for one Evan point?
You can use
I know Ed's got it.
You can pass it to a function. It can be produced by a function as a result.
Yes, but there's something very specific to it, and I'm going to let Ed answer it then, because he's really scratching over there. Okay, Ed, answer it and use the word state, because we like that word. Ed.
Function leads to no side effects. That it does not alter the state of the parameters passed into it.
That's exactly right. There is no global state. That's right. So when you have a function in math, functions are very easy. If I define a function for math, it takes input, f of x, returns something, 5, whatever, right? It's not pulling anything external to that. A pure function is a function like that. Here's the thing. The thing is, we're creating these things. I know you're going to object.
No, it's
okay.
just that, like, when you talk about, like, modifying something in pure math, the x, the value of x is what's changed. It's not changed, it's just replaced with a different value, okay? In programming, if you have that same function and you pass a variable in, you might be tempted to change that variable's value. You can't do that in a pure function. That's what makes it non-pure.
So you you have f of x, the x can't be changed? Is that
Let's say
the way it
X is an object,
Okay.
and you decide to, that object has a parameter in it called name. And let's say you decide to capitalize the name, modify its parameter. It's not a pure function.
Let me give you another way to reason about this, right? In math, you have functions. If those functions receive input, they're always guaranteed to produce the same output, right? If f of x equals 5, then if I call it 50 times at different times of the day, at different hours, in different locations of the world, I expect to get the same result back. Because
As long
the
as x
function
is the same for every
x, that's right.
Well, for every other.
But here's the deal, guys. When I say a function in programming world place, as computer programmers, that is not true. And that's a mistake to believe it for even a microsecond. So you have dates that can change. You can say something like date.now, it changes all the time. You can call things from a database. You don't know what the hell that database has got, or even if you have a connection to it, right? You have all different ways which you can call something function. Literally in JavaScript, say function this, and you have no guarantee that given the same input, you're going to get the same output. When I say it's a pure function, I mean that that is a function that's going to do that. There's no guarantee in the programming language because it's JavaScript, and JavaScript simply lacks a lot of cool shit. But it's there socially. I'm programming it to be there, right? I'm programming that function, so we don't use anything that is external to that function. We only look at the input, and we produce an output that doesn't modify anything else in the program. When we have this thing called village state, when we call village state with arguments, it's going to return us another village state. And that is substantial for the way we're designing this program, because the village state that it's returned is totally different. And if we ever call village state.move, we're always guaranteed to get the same output back. Given the same input, we get the same output. So let next equals first.move Alice's house is operating over this village state. This village state didn't move. Watch this. Next, right? Or rather, first.next. Like this. Oh, nope. First.move, I'm sorry. First.move, right here. Alice's house. I'm going to show you something. First, just so we all know what that is. First.move Alice's house. What's going to happen if I call this again? First.move again.
Same thing.
Same thing. If I call it again, same thing. It's not changing. Why is it not changing? Because it's not modifying first. It's returning to us a new state. Right? That gives you some advantages. It makes your program a lot easier to reason about. Makes your program much more resilient to bugs. It also makes it a hell of a lot slower and less efficient architecturally. So there's give and takes here, you know. But we like that in some capacity. So I just wanted to take note. Constructing a robot, right? But we're not going to get there yet. That wasn't the question. We're trying to figure out what these different arguments are. Ed's actually right though. So we'll get into what robot does in a second. But I want, you know, we had this question early on: how do we create programs? And I told you how we start to reason about creating a program. Well, now another question is: how do we reason about shit someone else created that's on, you know, using algorithms we've never seen before on a topic which we've never explored before, right? And this is one of the things that's going to help you reason about it. You see this thing called run robot that's taking 3 parameters: state, robot, and memory. You have to know what those 3 parameters are, or you can't reason about run robot. So we've determined robot is a function. What is memory?
That's your state.
That's exactly right. Memory is the state. Exactly right. What is state?
The location.
Memory is the robot's state, the history, whereas state is the package delivery needs state.
It's exactly 100% right. Say that one more time, Ned.
Yeah, repeat that.
Memory is the robot's state. It's history of what it knows and has done, whereas state happens to be the package delivery needs represented in that state object we just went through previously.
Okay, that's exactly right. Robert also had it right, by the way. Robert said state was what?
More states.
That's it, right? So Robert was actually, he knew right off the bat. He's like, state, oh, that's more state. Programmers see shit, and that's exactly what we think. Oh, that's state, that's more state, that's a function. That's going to do something with the state, and then it's going to save it somewhere else or return another. And that's exactly what it's doing, right? We're taking an action, right, which is the state from robot. So we give robot state and memory, we get more state back. And that's kind of how we think about this stuff. And we don't know what action is yet, but we'll figure it out later because we have action.memory. Memory is a property which makes action a object. So we know action's an object. So robot is returning an object. You give it state and memory. You get an object back. That object has a property, memory. Right? State, on the other hand, is the result of calling state.move. So we have this function, which we said was a method because it's on an object, move. Move takes a parameter, which is a direction, and it returns a whole new object. Doesn't modify itself, returns a whole new object, and that's what you're seeing here. State.move with the direction is returning a new state. Now, here's the key. What type of class is state.move? What type of class is state in this context?
Village state.
Village state, precisely. So we created a class called village state with a move method. That's a dead giveaway. Village state is the state here. We call run robot. We give it a village state object. We give it a function which knows how to do something, and we give it memory, right? Which is that what it's doing state, as Ed said, different state for different things. And then essentially that's what this does. This is a higher ordered function. Everyone go eat, and then we're going to continue to hash through this.
All right. Hope you all like the pizza. Ready to get back to it? Woo! There we go. Okay, so we just covered village state. Village state dot move is a what?
And remember, we use a special term. Pure. It's a pure function.
Yeah.
Right? And it's a pure function because anyone want to give an explanation?
It doesn't have
One input, one output, it's always the same.
It's not global. It's not global.
That's right. It's not modifying anything external, anything outside of its scope. It's not global.
That's exactly right. There are no side effects. All of that stuff is true. That's what a pure function is. So when we call move, it's going to give us back another object. That's kind of weird in the object-oriented paradigm. You don't see that too often. You see it all the time with functional programming. But with object-oriented code, most of the time, you're mutating state by changing the object itself. You're changing something in this, right? Because this is what holds everything. So when you call a method in an object-oriented language, you don't typically expect it to produce another object. You typically expect it to mutate its own state. But in this case, .move is returning to you a brand new object. So we just went over that. We called first, and I showed you what first equals right there. First is a village state object with a place, and it's got a list of parcels inside. And I showed you that when we call first.move, we're getting a new object back. We're not actually manipulating first. And then we did it 3 times, right? We did it multiple different times. And each time we got a new object back, right? So nothing's changing, nothing's funky. We get a new object back. Okay. So now they go into a quick little side note about object.freeze. That's an important side note, but they don't use it anywhere. It's really weird. But yes, you can freeze an object in JavaScript, which actually enables the compiler object. Call object.freeze and it makes it to our subsequent calls to set parameters, don't set properties, don't do anything. So object.freeze, value 5, we're freezing an object with a value of 5. We call object.value 10, and then we console log object.value, we get 5 back. Okay, and he says it helps him understand the reason about his programs, all of that stuff is true. It's just weird that we don't do it. So anyway.
It's just
critiques about material. We have this function run robot, and I think
critiques about material. We have this function run robot, and I think we started reasoning about what run robot did. We said it has state and it has memory. State and memory are both state. State is more state. Memory is state, right? However you want to cut it, we're making jokes about it. The point here is we take robot. Robot is not state. So we have state.
Robot is
not
a
state. Those
rehash function.
Robot
it's a function.
is
we know it's a function because we have this line.
We know it's a function because
right here,
we have this
right?
line
And that line is quite clearly a function. You have parentheses after a variable name, you know it's a
And that
function.
line is
Dead
quite
giveaway.
clearly a function. You have parentheses
So we're
after a
calling
variable
that
name,
function.
You know it's a function. Dead giveaway. So we're calling that function with two arguments, state and memory.
And from action,
And what we're getting
we
back
call
from
on the
that
memory
action.
which
And
is
from action,
the state of the robot,
we
which is
call
what
on the
Ed's
memory
comment was.
property,
Dead on.
Which is the state
I
of
asked
the robot.
everyone to
What Ed's
define
comment
state
was.
and
Dead
memory,
on.
and Ed gave us
I
a
asked
precise and
everyone to
accurate
define
definition that
state and
clearly
memory.
tells you the difference
And
between
Ed
the
gave
two
us
of
a
them.
precise and accurate
Memory
definition that
is the
clearly
state
tells
for the
you the
robot
difference between
function.
the two of them.
And state
Memory
is actually village
is the
state,
state
as an
for the
object,
robot
which is still
function.
state.
And state
Okay.
is actually village
Uh,
state as an object, which is still state.
So now what we're going to do
Okay.
is we have this thing here called random pick.
So now what
Now,
we're going to do is we have this,
I-
this thing here
like I
called
said,
random pick.
I don't
Now,
read books to you.
I
hope
like I said,
everyone that wants to read the
I
book
don't
did it on
read
their own
books,
time.
you know, I
But I'm not
hope
stupid because
everyone
I
that
asked for a
wants to
show of
read the
hands
book
last
did
time
it
and it was
on their own
depressing.
time.
So I'm going to make
But
the
I'm not
assumption no
stupid
one read it
because I
on their
asked
own
for a show of
time.
hands last
But I'm
time
going to
and it was
explain to you a
depressing.
different way.
So I'm going to make the assumption
We have
no
this
one
thing
read it
called
on their
random
own
pick
time,
and we need to know
but
what
I'm
it
gonna
does.
explain to you
We're
a
going to break it
different
down.
way.
We're not going
We
to
have
read
this thing called
because
random
no one here
pick,
wanted to
we
read
know what
anyway.
it does.
The vast
We're gonna
majority
read
of
it.
us. So let's take a look at this random pick
Because no one
thing
here
and let's
wanted to
figure out
read
what it does.
The vast majority of us.
We have this
Let's take a
random
look at this
pick.
random pick thing.
We're going to
Let's
pop
figure out
this
what it
over.
does.
Let's paste it in a
this
different
random
terminal
pick.
because
We're gonna pop
nothing
this
like
over.
messing up the one we got
Let's
and
paste
then
it
making
in a
monkeys
different
out of ourselves in front of cameras.
Nothing like messing up the one we got
Random
and
pick.
making monkeys out of ourselves in front of cameras. Random pick, what does it do? Well, we have this math.floor, math.random array length thing. What does math.random do? I don't know if we've ever seen that. Anyone want to give it a guess?
Gives you a number between 0 and 1, a random
Between
number.
0 and 1, let's confirm, right? We pop it in here, oh, that's exactly right. Between 0 and 1, that's what we're getting back. So now we're multiplying it by array length. Well, why in the crap would we be doing that? Anyone want to take a guess?
Yeah, if you're randomly going to pick an element, or if you'll pick an element.
Is it like coordinates?
Because you're using that math.floor, so whatever the array length, instead of a number between 0 and 1, which you multiply that all, if you have an array with a length of, say, 9, that'll give you a random number between 1, 2, 3, 4, 5, 6, 7, 8, 9. That's what that's going to give you. It's going to give you a random choice of all the elements within that array.
That's more or less, we're going to go over that. I like that. That's not bad. There's nothing about that that's wrong. But if you didn't understand that, I hope I'm going to help you understand that. Okay, if I call math.random and I'm getting a number between 0 and 1, right here. Robert, do you ever get 1? You never get 1, right? We went over some of this stuff earlier and people asked why, and I said, look, I really don't want to go into that crap. 1 is exclusive. 0 is inclusive. You can get 0, I believe.
One thing.
Yeah. You should, because remember, you look at all these numbers, right? See all those numbers? In science, we call them significant digits. You see all those digits there? The chances of you getting 0 are infinitesimally small. I probably never got it in my life. And I've also never won the lottery. But the point is, you can get 0, as far as I know. You can never get 1. One of them is inclusive, one of them is exclusive. So we have a range here. And that range can never be 1. If we multiply whatever we're getting, which is 0 to 0.9 continuing, by 2, what is our range?
0 to 2.
0 to 2, right? We've increased the ceiling. The floor stays the same, because you can always get 0. Multiplying that by 50 still gives you 0, but you increase the upper range on that. So when you take a random generator, like math.random, you multiply it by something, you're actually just giving yourself a different ceiling. And here's the cool thing about it. You have equal dispersion throughout. So if you take math.random and you multiply it by 2, you now have a ceiling of 1.9 repeating, right? Now, if you call floor on that, what are your potential values? Floor is actually going to drop everything after the 0 and truncate it down to 0. That's what floor does. So if you call floor on 1.1, you get 1. If you call floor on 1.7, you get 1. Now, you might say, well, how the hell do I know that? Well, let's give it a shot. Math.floor, 1.1, 1. Math.floor, 1.99, 1. There's your, just try it, right? That's what Node is good for. You have the whole bash on tab shit when you forget the name. You also have try it and see. These are not questions for Stack Overflow. These are try it and see things. So we essentially are multiplying math.random by a number to change the ceiling. You multiply math.random by 5, the ceiling is now 4.9 repeating. The lowest you can get is 0, right? If you truncate that down, what are your potential outcomes? Your potential outcomes are
0.
0, 1, 2, 3,
4.
and?
That's it.
That's right, that's it. You don't go higher than 4, right? You don't go higher than 4 because you can't get 5 point something when you're just multiplying it by 5, right? You're multiplying 0.9 by 5, you can't get a number greater than 5. So we've reasoned about random pick. Random pick takes an array, generates a random number, multiplies it by the array length, which increases the ceiling, right, of that random number, and then it truncates it back down to 0. Why is it doing all that stuff? Because you just want a random thing out of the array. That's a way to generate a random thing out of the array.
The
So
lowest number is 0, and the largest number is array length minus 1.
That's exactly right. And why is that convenient? Because what do arrays start at, guys?
0.
They start at 0. So if you want an array length, right, if the array length is 5, the last thing in the array is 4, because the array started at 0. So an array that has a length of 5 starts at 0 and ends at 4. Okay, just rehashing over some of this stuff. I know we've heard that a million times by now. Now we have this other thing, random robot. What does that do? Okay, well, we know what random pick does now, right? Takes an array and it just grabs us something random from it. And we know what road graph is. Okay, some people are asking questions. Some people don't know. So let's go back here and we're going to type in road graph, right? Boop, boop, boop. Okay, road graph is this thing here where we call build graph on roads. Build graph is here. We saw what that did, right? So these are the roads. The roads are begin dash end. We never use them again. We generated the graph and we were done with the input. And by the way, when you use a graph database, that's always what happens. You tell the graph database that your father is Bob, whose father is Fred, whose father is Tom, and then you're done. And now you can just say, let me see all of Tom's grandchildren. Right? You don't keep the original things you use to get that data in there. So roads is gone in our program. We have used roads to build a graph. Road graph is the graph we've built. Okay, coming back, we have random robot. Random robot is calling random pick on road graph. Right? Okay, let's come down here to road graph. Let's clear that up. Road graph. Nope. Come down here. Actually, I'm going to paste both of these here.
Excellent idea.
Whoop. Okay, now we have both of those functions. And now we're going to look at road graph, right? Make that a little smaller. This is road graph, right? So, actually, that's it's not road graph. There's road graph. That's road graph right there. Road graph is an object, key value. We have here Alice's house. Alice's house has an array of places we can get to from it. Random robot is taking a state. Presumably that's village state, right? And when it takes that village state, it looks at the state.place. This is where you're at. Right? I told you I like to and from. This guy likes changing them a lot. So we have state.place and state.addresses. State.place is where you're at. State.addresses is where you're going. Right? Okay. So state.place could be any place we're at. And what we're going to do is look up wherever we're at in this road graph object, right? And that's going to give us something like one of these value arrays, right? There's all different value arrays we've got, but we're gonna get whatever one that represents where we're at, and that's going to tell us where we can go. And now what are we going to do with it? We're going to pick one of them. No rhyme or reason, just give me one. That's the dumbest robot you can implement. But it's fun and it's easy, and I like that. And things get really hectic from this point on, right? Because making things not dumb and not easy is definitely the corollary, which is, hard and smart, and that's at the point where you're no longer focusing on JavaScript or programming, because you're getting into the wonderful world of math and algorithms and graph theory. Okay, which if anyone was here at the very beginning of class, Ed looked it up, what type of algorithm it was, and
Extra unweighted pathfinding algorithm.
or so he says.
That's right.
Yes.
That's right.
He could be right. I don't know. I've seen Dijkstra's algorithm. Remember when I said we write these programs in the real world, which we do frequently. We don't know how the code works frequently. Most of us don't look at the libraries we use. I certainly don't look at the majority of the libraries I use. It's literally copying and pasting, except we gratify ourselves by saying we're using a library. But it's essentially the same thing. So when we use a library in the real world, when we do this problem, we tend to use something like PostGIS, which is a spatial extension for Postgres. And on top of that spatial extension, there's something called pgroute. And pgroute is actually how you would do this in the real world. You would never do this problem in JavaScript. So if you want to build yourself a Google Maps when you go home that can tell you how to get from cPanel to your house, which we could do in this class, you would actually use pgroute to do that. And it would literally do all of this stuff under the hood, polished and better. Okay. So we have this thing, run robot, and essentially we can call it with villagestate.random. Well, let's look here. Here's villagestate.random. Let's go through what this is doing. Villagestate.random takes a parcel count, right? You can give it whatever number you want. And what it's going to do with that number is it's going to call random pick on object.keys.roadGraph, right? Now, object.keys returns an array of keys that it generates by looking at the object. So if you have an object, you have a bunch of key values, you call object.keys, you get all of the keys in an array, right? So let's look at this, and let's actually call this. Why are we calling it? Because I want to show you how we take apart what other people's code does so we can make sense out of it. Okay, there's one. Let's call it again. There's another. There's another. It doesn't matter. I can keep calling it all day. It's a lot of fun. And I get a different one of these, right? Let's take a look at it one more time. Let's say, oh, how does that work? Well, let's come down here. We're going to call object.keys roadgraph. And there's your array. So you want to pick one out. You just do that. Random pick. That function we made. Now you get one of the places that you come from. Okay, so we're generating an address, which is a place, and now we're saying for each one of those places, right, for the place that we generate, what we're going to do is we're going to create a parcel for it, right? So essentially, a parcel has a place where you pick it up and a place where you drop it off. That's what he calls a parcel. I don't know that he explains that in there, and I don't know that he explains anywhere how you represent a parcel, right, or what the parcel object looks like, but clearly that's what's happening. We have a parcel. Parcel says, pick me up at this town, drop me off at this town, or this house, or whatever cute little thing he's got going on here. And what we're doing here with this do while loop is we're saying, if we just so happen to pick the same two things out of that road graph array, then just generate another one. Right? That's probably because we don't want to handle the condition where we have a parcel that you pick up and drop off at the same house. Because our robot at that point would have to decide whether or not he gets out of the car and goes back into the house, or whether or not he's literally randomly going around the whole network again. And then we would hope that if he did do that, he wouldn't pick up another parcel that had the source and destination set the same. Otherwise, it's just a lot of stupid work. So this is literally just solving that edge case. The edge case is we generate a parcel with the same to and from. So we solve that. In fact, if we just ignore that edge case, having had it explained, it becomes a little bit easier. So we pick an address from that list, and we essentially say we're going to create a new parcel with it. Right? That parcel is going to have the address here. And actually, this is it. So that's why that was useful. That was useful because we generate the place too. So if we ignore the edge condition, this is what that looks like. And that may make more sense. Let address equals random pick, object keys, road graph, get a place. The same thing with place. And then we've generated this parcel object right here with a place and an address. And then we push that onto an array of parcels. And we are generating however many parcels we give it as an argument. So we default that to 5, which is what that syntax does. If you don't remember that syntax from the function world, when we say function argument equals 5, it means default that argument to 5, right? If you don't provide an argument value, you get 5. If you do, the 5 is ignored. Okay, so we're generating a village state that is starting off at the post office. That's where we start off at. And it has however many parcels we give it in parcel count, or 5 is the default. 5 parcels, which include a place where we pick them up and drop them off. Parcels could probably be better called tasks because they're things that we need to do, right? It's probably not a good idea to call parcels parcels because you're going to think of them as a noun. Most of the time when you're writing a program, you will engineer this differently. You would use the word task because there are 5 things to do. Pick up from A, in fact, pick up underscore from would be better. Drop off to would be better, right? There are 5 tasks with places we start and places we end. Okay, and we start off at the post office. So we take a look at this, and we've explained run robot. We've explained what random robot does, right? Random robot is right here. It's just this, picking out a random place that we can go to, and if we can go to that place, we're going to pick up parcels from it or drop off parcels to it, and we're going to keep doing this until we exhaust all of the tasks we have, right? So we call run robot, we generate a village state.random. Actually, I didn't have that code. Let's copy this over. Village state.random, that's what it looks like. Start from the post office, and here's our 5 tasks. We're going picking up from the post office, dropping off at town hall, picking up from the farm, dropping off at town hall, picking up from Ernie's house, dropping off at the farm, so on and so forth. That's our random tasks, right? That's what the code's generating. And here's where we call run robot. Well, I gotta learn to copy code. Okay. And there you go. That's what our guy's doing. So from a random state, we're moving to the marketplace, the shop, Greta's house. Each time we do this, we could be picking up a new package or we could be dropping a package off. But we just keep on doing this until we complete. We've done all of our tasks, and it tells you how long it took you to do it, 51 turns. We can do it again, and it takes us 53 turns, so on and so forth. Each time we do it, we generate a new list of tasks, and we move in a random order to complete them. So you could do this 10,000 times, and you could find out, what the average amount of moves you have to make with a totally random algorithm would be. Okay, so now we have learned how to make sense out of location, graph data, edges, and we have done something totally stupid with it. We're moving randomly. In the next part of the project, we make sense out of this by moving in a logical fashion. And in order to move in a logical fashion, we actually have to have a means to get from the starting point to the ending point in the shortest path. You have to have some idea of an intelligent method of doing it, right? So we come down here. We declare a constant mail route. Let's see here. Yes. Before we do this, hold on 1 second. I'm going to show you this. See, they have this run robot animation thing. This is kind of cool. I'm going to show you this. I like this. If you're going to give something bizarre like this, it's really cool to give something fun too, right? So this is the place he's got. And each one of these is the first letter of that place. If we come back here and we look at the
project list, we can see right down here what all these places are. And how we got that is we called object.keys on the graph, right? When we wanted to find out all of the different places we could come from or go to, we called object.keys on this graph we generated, road graph. So object.keys, come on. Object.keys is going to generate us like this, a whole list of things we can do. And now what we're going to do is we're essentially going to travel to them. And if we look here at these different letters, A is Alice's house. This is obviously a cabin. That's C, right down here. The post office has got to be P, which is right here at the top. It says post. Okay. So we say run code. And you can actually see this work.
Cool.
So we are actually learning how to program that. There should be your aha moment. That's what we're doing. We create a graph, and now we're learning on how to pick up and drop off packages. Watch it again, because you can actually see it pick up packages. You see how it picks them up? See how A, B, A, T, A, now A, D, D gets dropped off at D. There you go. So he picks up a package. The package has the code of where it needs to be dropped off at. So you see him randomly moving to different houses. He picks up a package. If that little box says D, then he's got to drop it off at D. Let's give it one more shot here. He just picked up E, M, T. He's just dropped off S. I can't even say it as fast as it because he's got to move sometimes 15, 16 times to get this thing done. Okay. So yeah, that's kind of cool. Now we have mail route. Mail route has got essentially what we're doing now is we're saying, okay, we have different methods of solving this problem. Let's talk about them. One of the methods we can solve the problem is we can find a route that hits all of the possible places, and we can pre-establish it. Then we just have to connect to that route, and the worst case is we have to move around it twice. Right? The first time to pick up the packages, and then the second time to drop them all off. That's another method we could solve this problem. So if your city happens to all be around one big loop, then Amazon would only ever have to drive around it twice to pick up all your returns and drop off all their shit. Unfortunately for Bezos, he's got to work for his 160 billion, or the slaves underneath him do. He doesn't have to do anything. Okay, so what we do here is we have this function route robot, and route robot is taking a state and memory. State and memory are both state. That's right. And we're saying if memory.length equals 0, if there is nothing in memory, then what I'm going to do is just simply return this direction and memory to be the first element. Right? So in robot memory, the robot keeps the rest of the shroud in memory, drops the element off at every return. What I want to see here is where is route robot? One second. Aha. Okay, here's what we're doing. This is the catch. This is what I missed. Route robot is initializing its internal memory to the mail route. The mail route is this thing right here. Mail route has the loop. So when you call route robot, if you don't have anything in memory is an empty array, then you initialize it to the mail route. This is bad programming style. Just that, Robert, you know why this is bad programming style? You wanna say it? Does he say it too?
It's like it's a hidden site.
This is the reason why I would say it's bad. It's bad because here's where you're initializing it, right? You initialize it right here. Why couldn't you just pass mail route right there and then get rid of this entirely? I don't know the answer to that. Run robot is taking the state of the village, the thing that you're using to traverse your graph, which is route robot, and it's taking this starting memory. The starting memory could have just been mail route. But anyway, what we're doing is we pass it an empty array. We detect if the array is 0, and then we...
The reason why the starting memory is empty is because when we do the more optimized non-random solutions, we're going to have to remember we've already went through a place, and so we're going to try to...
Or mail route might be out of scope.
Mail route's a global.
I know, but if you were to put it in a class, it could be absent.
Maybe. We can all speculate. I wouldn't never like that. Okay. Yeah, I agree. There's definitely, it could be because in the future we want to expand upon this. It's not because I've read the lesson. It could be because it's a global and maybe he wants to leave you the ability to write it here. I don't know. But the point is, he detects whether or not this array, which we know we're sending in is empty, is 0. And if it is, he sets memory to mail route. And then he continues. And he says, give me the first thing off of mail route. Each time, slice. What does slice do? Slice is not pure, right? Actually, in JavaScript, it is. That's not true. In JavaScript, it is. If I say let a equals 1, 2, 3, and I say a dot slice 1, you get 2, 3. That's what's happening. We're saying when we give it this loop, right, the first point of that loop is where we need to be. We got to get to that first point, which is memory 0. Mail route 0. And then the memory where we have to go on that loop is the result of slicing off the first value. Slice drops off whatever value you give it and keeps going for the rest of the array, copies the rest of it. So if I say 1, 2, 3, 4, 5, whatever, and we say a dot slice 1, you're going to get the rest of it. You're slicing off the first element. If I say slice 2, you're going to chop off 2 elements of it in the beginning, and you get the rest of the array. So the slice is going to return whatever isn't chopped off by the call, right? A new array that represents that. Is that clear to everyone?
Yeah.
Okay, I just want to make sure that we're all following along with slice. Slice
You
is
slice by the
returning.
comma, you get the numbers.
Say that one more time.
If you slice per comma, would you get all the numbers?
So, no, not in JavaScript, but you would in some languages like Python.
Oh.
In JavaScript, you automatically get the rest of the numbers when you slice. So when you slice 2, you're pulling 2 elements off, and you're getting the rest of the array returned as a new array. If you slice 3, you're taking off 3 elements, and you're returning the rest of the array. Right? So the reason why you do this is you say, I want to, if you do pop, what does pop do?
Takes off the end.
Takes off one element from the end, right? Now there's also something in here called shift and unshift, right? What does unshift do?
Takes it off at the beginning.
Takes it off at the beginning, right? But what does unshift return?
The rest of the array.
No, unshift returns the element you take off.
Yeah.
Unshift returns the element you take off. So what's the difference between array.unshift and array.slice1?
Your return value.
Exactly. If you unshift an element from the array, you're removing that element from the array, the beginning of the array. If you slice one element off the array, you're getting back the rest of the array without that element. Right? So if I have 1, 2, 3, and I call unshift, I get 3. Actually, this is explained by the way. No, that's really weird.
I thought shift was back. I thought shift was taking it off and unshift was putting it on.
That's what I thought too.
Okay, that's actually right.
Yeah.
Shift is taking it off, unshift is putting it on. That's right. So today I learned if you call unshift with nothing, you get 3, which is probably just counting it or something. I don't know. That's a different question for a different day. Also, JavaScript is weird. 1, 2, 3 dot shift is going to return the first element. That is correct. I made a mistake. I erred. Pop pulls the element off the end. Shift pulls the element off the beginning. Unshift puts an element on the beginning. Push puts an element on the end. If you call shift, you're getting one element from the beginning of that array. That's what it's returning. If you call slice 1, you're getting everything but that first element. Right? So what we're doing here is we are making the first place we're at memory 0, which is the first part of that loop. Then memory is going to be set to everything that's not where we're at, right? That's left. So if we look here, I just want to show it to you. You may say, okay, well, how do we always get to 0? Well, we always get to 0 because 0 is always accessible by the post office. So we're always starting at the post office, and 0 is Alice's house. Alice's house is right here. So Alice's house is always connected to the post office. Let's go through the loop and I'll show you where we can go. We start off at 0, the post office. We go to Alice's house. Where's 2? 2 is the cabin.
Cabin.
So we go from Alice's house to the cabin. Where do we go from the cabin? My PayPal. No. Where do we go from the cabin?
Bob's house?
We go from the
Alice's
cabin,
house?
Alice's house, right? We're
Yeah.
going backwards. So we go
Huh.
post office, Alice's house, cabin, Alice's house, then where do we go?
Bob's house.
Bob's house, then where do we go?
Town hall.
Then we go to town hall, and so on and so forth. That's how this graph is working. So every time we call this thing, whatever this thing, route robot is saying, I'm at the first location that's left, and then I need to go to everywhere else. And then when you call it the second time, it says, I'm at the first location that was everything else, and now I need to go with everything else from that. You know, and then that's how it works. It works through it like that. Okay, so we have this route robot, and now what we're going to do is we're going to call this, which is different, right? Before we were doing this random thing. Here, guy, can I get back to it? Always my problem here. So before we were doing this, run robot. We were calling run robot with village state random and random robot. Now we're going to be calling it with route robot and giving it an empty list. So let's call it with route robot and let's give it an empty list. Okay, let's go through this one more time. In the book, this is also I think slightly weird. He's doing this run robot animation thing. This isn't in agreement with any of the code inside of the book, right? Inside of this chapter. Run robot animation is code that he gives you in the code sandbox, which is something he provides. It's this thing, right? This is run robot animation. It's this cute visual display of it, right? So when we call run robot animation with random and goal-oriented robot, we get that code that I showed you in the class. This is using the shortest path method. We also have this, right here. This is the random method. So we can call that run robot animation thing. Now remember, with the smart method that we started with, we did it with 9 turns. I wanted to show you how this worked. Let's do it with the dumb method that we first got, kicked off with. Okay, that's going to take a long time.
Yeah.
Right now, look at it. It's literally, hey, it's just go moving all over the.
It's getting tight.
Moving randomly.
It's moving randomly, right? So that's a visual display of the robot doing the first thing we did. That's kind of cool. I think he should have shown all of that code in the boilerplate. I should have started off showing you the random one so we could take you through and show you our optimizations on it. But let's just stare at it for a second because we all like flashy lights and pretty 8-bit graphics. So that's the random method, and now what we're doing is we have created this new thing, right? We're using this new method, which is no. 1 second. There we go. It's this root robot, right? And root robot moves in a circle. So random robot just finished. Yay! Random robot just finished, and now what we're going to do is we're going to use root robot, which I can't copy either because I'm stupid. We're going to copy this guy right here, and we have root robot now. So you just saw random robot. Here's root robot. Now we know root robot is moving in a circle, and it's going to go through that circle how many times? Twice. At the most, right? So let's give it a shot and let's see what it does. We should expect it to move in a circle. And there you go. There's the second time it's going to go through the circle. So here you guys all thought that Tesla was doing something worth billions of dollars, and it's just a little JavaScript program, right? Self-driving cars tomorrow. Okay. That's right. So we've seen now 2 robots. We've seen the random robot and we've seen the loopy robot, and now we get into this
what I consider like probably too complex for JavaScript classes. We have this thing called find root. Okay. I'm trying to figure out whether or not I want to explain it. Do you think?
Can I try to explain it in simple English?
Go for it.
All right. So what this does is it basically says, where am I, and where do I need to go to? And it adds every possibility of every way it can get away from where it is. And then from every one of those states, it adds where it can go to from there, and so on and so forth. But since it's adding these steps one at a time, it's growing the length of all these possibilities one at a time. As soon as it finds a possibility that satisfies all the conditions of hitting every place that they were going to, then it stops. So a lot of these possibilities that exist out in the future are not considered.
Or maybe in simpler terms, it's like it draws a circle around itself, an expanding circle. And when it finds, the first time it finds the destination, that's the shortcut.
It's doing a lot of stuff. The reality is that it's simply doing a lot of stuff, and none of it's related to JavaScript or programming concepts. It's all related to graph theory. Like this part right here where it says and not work sum, right? This is called non-backtracking. So it's making sure that the places it's going to are in places that it's already been, and that's a really way of writing that, but whatever. The point is that this is essentially doing what I just said, and that's it. You know, you don't have to understand this code. If you're interested in graph theory, perhaps we should teach a class on it. This is not the right one, despite what some people think. So we're just going to copy it, right, and take it for granted that you're providing it a graph. You're providing it where you're starting from and where you're going to. It's doing some pretty clever stuff, or sort of kind of clever stuff, depending on who you are, and it's going to give you back a result. So we pop this find graph over here, and if anyone wants to hash this out at the bar, that sounds like good drinking stuff, I guess. And we have this thing called goal-oriented robot. What is that doing? Well, we know it's calling find route, so it's doing something smart, or semi-sort or kind of smart, depending on who you are. It's calling it twice. It's saying if the parcel.place is not equal to place. What does that mean? Well, you're providing it an object, a village state object. That village state object has two things in it. It has a place and it has parcels, right? And what we're saying here is if the place that we're going, right, which is the first parcel, parcel.place is the first parcel in that array, the first task we have, if that place and the place we're at are not the same. So the thing here is that we don't have to go anywhere if the task we have is where we're at, right? We generated tasks, and if you guys remember, I said in the event we generate a task that starts and ends at the same place, right? Skip it, because it creates a really weird edge case for our system. So I said if we generate tasks, we generate these parcels, and they're to and from the same address, we simply skip it. That's what the village state.random thing did. Okay, well here, we're catching the case that we're starting at the post office, right? And we have something that needs to be done at the post office. If you do something like that, you don't need to move. You just need to do work, right? And the same thing is true for each and every step on that graph. If you get to that graph, and you're looking at the first parcel you have, and it's work that needs to be done, you need to do something different, right? So we handle that. Anyway, we have this goal-oriented robot, and it's using this find route stuff, and we're going to pop it right down here. And essentially, this gives us the ability now to generate what amounts to a shortest path with a random starting point, which has our random packages in it. Okay, run, that's because this is, again, run robot.
I read the PDF version of the book, and it's a little confusing.
Can we explain this?
No, never mind.
I don't. Oh, you mean because it has the run robot animation?
Maybe I just didn't understand it.
Yeah. The thing is, like, I mean, I don't mind explaining like the algorithm stuff. I just don't think it's at all relevant to becoming a computer programmer or anything of that sort.
Well, algorithms in general, but it's not going to help you understand the JavaScript in this case.
Yeah, and it's also, if you want to be a math person that literally writes algorithms and finds optimizations, by all means, go at it. Have fun. It's a blast. It's a lot of fun. You can learn about trees. You can learn about all of these types of things come up in it. And the question is just simply, how much of that do you want to teach in a class that's trying to introduce you to programming concepts in JavaScript, which are simplistic languages with basic concepts that are evident everywhere. And I think teaching how to implement a graph database is a pretty steep order. But this run robot thing, we can see what we're doing now. So now we have a smart method of doing it, and we're down to 20 turns. We're down to 9 turns. We're down to 14 turns. Our best case scenario is substantially better with this method. 6 turns. We got one with 6. Remember with the loop, we have to go around at most twice. That's our worst case scenario. When you work with algorithms and you do that, maybe he talks about it, you focus predominantly on your worst case scenario, right? And you do that because if your worst case scenario is the world ends, you need to think twice about how you implemented the algorithm, right? Generally speaking, containment of catastrophic effects is what you want when you're in IT or you're in programming.
Could you say that sentence again? Sorry.
So there's another consideration too. I mean, he's talking about safety. If the program misbehaves and people die, then that's probably an indication that you need to use better safety in your algorithms. But one problem with algorithms is their runtime complexity, or how long they take to run. If your program is just chugging away, but it's going to tell you which class you can register for in under or slightly over 2 years, then you've got a time problem. It's still correct. It's just that the information will arrive far too late to be of any use to anybody. And so, generally speaking, many people don't start off with big enough data sets to worry about it. They don't start off with complicated enough processing to worry about it, but once you add up 2 or 3 loop-like lookups, the next thing you know, things can take a long time. But studying algorithms really is something that's probably better done in a class by itself.
That's dead on. Full agreement. It's a useful thing to do. It's really cool to learn. It's better done in a classroom setting. Perhaps we may want to do it here. Then people have a demand for it. But it's probably not best to muddy that with what we're trying to teach here. So I wanted to recap on what I was getting at. You have 3 different dynamics when you talk about algorithms really quickly. Best case scenario, average case scenario, and worst case scenario. Those are your 3. Best, average, and worst. Those are the ones you focus on when you work on an algorithm. You want to know, yeah?
Common case.
Okay, I stand corrected actually. Common case is actually probably more important than average case, but yes. So you have 4, right? But the point that I want to make is that by far the most important one, I think that would be in anyone's eyes that develops algorithms, is worst case scenario. Right? Worst case scenario is the big one. Because if there's a 1 in 100 chance that the world blows up, you have a real big problem. Even if it's otherwise lightning fast, 2 times faster than it would otherwise be, the world blowing up is a big problem. So when we look at these 3 different algorithms we have random, we have the circly loopy method, and we have the shortest path method. All of them have different profiles for best, worst, and average, and average and common case. Right? They all have different profiles for that. Now, in the loop method, we know that the worst case is we're running around the loop twice. Right? In the shortest path method, we know we have the best case scenario. Because we may not even have to go around the loop once. Maybe there are only just 2 places. We just go 1 loop and then we're done. We had one of them that was 6, right? Right here.
That's not even visiting every location on the map.
Not even visiting every location on the map with that. That's a really damn good best case scenario, right? So we have these different profiles, and when you take an algorithms class, you will learn to think about problems in that sense. We're not doing that. So I just wanted to show you that we went through 3 algorithms. You can all figure them all out. Random case is haywire. Worst case, you could be, I don't know, what's the worst case for a random problem? I don't even know the answer to that. I guess you can keep generating the wrong number and do it for
Infinite?
you know.
Well,
you're confusing.
just shy of it.
Just shy of infinity. The worst case scenario on the random problem is it doesn't finish in your lifetime.
Yeah.
And it's a very slim chance that happens, but it's still definitely a chance.
So like on a random one, there's a problem in computer science that decides whether or not something is computable. And it's been proven that there are certain non-solvable answers. So like our random algorithm is subject to something called the halting problem. And that is that you cannot prove that a random algorithm will ever finish. So the worst case scenario in a random algorithm is unbounded.
Right. Which is what I was getting. It's like I think Robert said, it's one away from infinity. You know. But yes, the point is that
Infinity minus 1.
No, is
infinity, yeah. Because one away from infinity is in fact infinity. So you can reason that another way, right? I think that's actually true. Anyway, I don't do math, so by all means, ask them. But the thing is, I think we have now an understanding of how we write this. We have an understanding about the run robot thing. We have fed it different values. We have an understanding of the state which we stored in memory and the state which was the robots. We showed that. We demonstrated in the loop. The state is the loop. As we iterate through it, the state for each one of those actions is the rest of the array, and we move to the first. Right? We go to the next element, and then we have to go to the rest of it, which is the loop. And then we go to the next element, and we have to go, whatever from there on as we complete that loop. That's what that second state variable was. The first state variable, village state, we start off at the post office, and we're simply generating 5 parcels, or as we would more intelligently call them, tasks. Each task has a to and a from. We iterate as we go through, and we crawl that graph. We start to solve those tasks, picking up and dropping off packages. Okay. I don't know if anyone has any questions. We totally didn't touch at all any of the original text today. And we just focused on the code, which is a totally different approach than we normally take, where we at least give some reading to the code, to the text. But we did that because, as goofy as some of that code was, we could still reason about it, right? And I kind of tried to show you how we would do that. And hopefully that all starts to make sense, and when you're going through the Linux kernel, you can use some of those same tricks and knock yourselves out, because it is still the Linux users group. Okay, I think we're done. We've had people have requested us close up earlier, so I think we're going to shut it down. If anyone has any questions, that's great. If not, I guess do we have demand for another one? Are you guys enjoying this? Because it's getting, the classes are getting more and more like
Good stuff.
we're doing graphs and stuff. I don't know if we want to keep it up, but
But even though you're doing graph, we're reinforcing a lot of concepts like functions,
so it's good.
applying methods to them.
okay. Well, the next class is bugs and errors, which is everyone's least favorite subject.
Debugging.
And like Adrian Silva, everything the rest of them.
We want one more class so we can really get upset with people.
I think that we should. I think that actually we're going to definitely do this. I've decided.
This is important.
This is
because
important.
You need to be
Yeah.
able to handle mistakes in your program, because you will eventually introduce mistakes in your program as part of building it.
And I will actually say this. I'm actually looking forward to the rest of these, because looking at the list of classes we have after this is getting better, not worse. So bugs and errors is very important. Regular expressions is extremely important and very fun in my opinion. And I look forward to that. Modules is super practical and exploring Node actually makes sense as a system. I'm going to take a look at that and decide whether or not I want to hit that like the book or hit it my own way. Asynchronous programming is also super useful. Yeah, so I guarantee you this though. Part 2 browser. I'm not sure that we're going to do that. That to me sounds a little goofy. So I think we're going to finish bugs and errors a lot quicker.
Well, the DOM is going to be incredibly important in the events underneath the browser introduction. It's going to be incredibly important. If you ever intend to use JavaScript inside a web browser, which is traditionally its strongest
Use case.
Yeah, that's the strength.
It's really a call whether or not people want to learn the applications of JavaScript. I will tell you this, the class got started because it was suggested that people learn with C, which is something I, as a C programmer, am not a huge fan of, because it's a very rough, it's hard, and the payoff is not there in my opinion. So JavaScript is a better method to teach computer programming than C. Python's also very good, I don't have a problem with that, but I wanted to teach computer programming. And the second we get into DOMs, we're not teaching computer programming. We're teaching how to do stuff, specifically how to control the browser and rendering and events. And that's cool, but that wasn't part of the original mission. So if people want to do that, I guess we'll march forward with it. It certainly is one of the biggest things JavaScript does.
Do we want to see after JavaScript?
Well, you know, I think we could revisit the C and teach C. We probably won't go into as many of these lectures as we've had in JavaScript already. Because even though C may be not the first tool that you reach for, it teaches you about the generic machine model and how memory is handled. And even if you don't actually ever use that directly, every programming language that you use interfaces at that kind of a level. And so like certain things that you do, like how did you know that the returning back the extra copy of the object was a lot slower and a lot less efficient? It's because you think, like a C programmer, you realize that it's a different allocation, a different memory reference that you've got to mask map.
It definitely helps you understand the machine. There's no disputing that. The thing is, simply, it's not very good for teaching recursion. It's not very good for teaching things like closures. It's just, the syntax for it is super weird. And it's not useful anywhere else. There's just so much stuff in C that I think is like edge case, corner case, and 30 years of legacy. But yes, if you want to learn the machine, I think it's good.
Is there a good book for C that we can learn for ourselves if you don't want to teach it?
Yes, I have an excellent book, one that I highly recommend if you want to learn C. It's called C, A Modern Approach, I believe. It's by a guy named King. And it is definitely, in my opinion, the best book for learning C. It's 800 pages. It's a great read.
We can cover it chapter by chapter.
This is your own version.
I mean, I actually, I have it right here. If you, but I mean, it's like it's so much of that is like if I was to teach it, it would be way too in the woods. You know, you would start in the woods and you'd end in the woods. That's C. Okay. So moving on. Yes, I think we'll definitely do bugs next week, and then we'll start. And we'll definitely do regular expressions the week after, and then we'll figure it all out after that. Cool.